Imagine worlds orbiting distant stars, each a new opportunity to find life beyond our home planet. Exoplanets are at the forefront of this cosmic quest. Exoplanets, planets outside our solar system, have become key players in the search for extraterrestrial life. Since the first confirmed detection in the 1990s, thousands of these distant worlds have been discovered, ranging from scorching hot gas giants to potentially habitable rocky planets. Scientists focus on certain characteristics, such as location within the habitable zone where liquid water could exist, atmospheric composition, and planetary size to assess their potential to support life. Advances in telescopes and space missions like the Kepler Space Telescope and the James Webb Space Telescope have enhanced our ability to detect and analyze exoplanets. By studying their atmospheres for biosignatures, such as oxygen or methane, we hope to find evidence of life or conditions suitable for it. This pursuit not only fuels our curiosity, but also expands our understanding of life's diversity and resilience in the universe. As technology progresses, the study of exoplanets brings us ever closer to discovering whether we are alone in the cosmos or part of a grander, inhabited universe. When we talk about exoplanets and the search for life beyond Earth, one concept that stands out as absolutely crucial is the habitable zone. This zone, often referred to as the Goldilocks zone, is the sweet spot around a star where conditions are just right, not too hot, not too cold, for liquid water to exist on a planet's surface. Why is this so important? Because water is the foundation for all life as we know it. Without liquid water, it's incredibly unlikely that life could develop or sustain itself. The habitable zone depends heavily on the type and size of the star the planet orbits. For smaller, cooler stars, this zone hugs close, while for larger, hotter stars, it's much farther out. This makes identifying the habitable zone a dynamic and star-specific challenge in exoplanet research. Scientists use the habitable zone as a primary filter when sifting through thousands of exoplanet candidates, zeroing in on those worlds that might actually support life. But it's not just about distance. The planet's atmosphere also plays a huge role in regulating temperature and protecting liquid water from freezing or boiling away. This means even planets within the habitable zone might not be hospitable if their atmospheres are too thin or thick, or if other extreme conditions exist. Understanding the habitable zone, therefore, is a cornerstone of exoplanet science. It helps us focus our search and resources on worlds that are promising candidates for further study and potentially life itself. As we refine our detection methods and learn more about different star systems, the concept of the habitable zone continues to evolve, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe? Detecting exoplanets and peering into their atmospheres involves some truly ingenious techniques that astronomers have developed over the years. One of the most successful methods is the transit technique, which observes the tiny dimming of a star's light as a planet passes in front of it from our viewpoint. This subtle dip gives us a wealth of information, not just that a planet is there, but also its size and orbit. When multiple transits are observed, scientists can precisely determine a planet's characteristics and begin hinting at the possibility of an atmosphere. Complementary to this is the radial velocity method, which detects the slight wobble of a star caused by the gravitational tug of an orbiting planet. By measuring shifts in the star's spectral lines, astronomers infer the planet's mass and orbital period, crucial data for understanding whether that planet might host conditions fit for life. But to really understand if a planet can support life, it's essential to analyze its atmosphere, which is where spectroscopy comes into play. When a planet transits its star, starlight filters through the planet's atmospheric layers, imprinting unique chemical signatures onto the light spectrum we receive on Earth. By decoding these signatures, scientists can identify molecules like water vapor, methane, carbon dioxide, and oxygen, key ingredients that could signal habitability or even biological activity. Advances in telescope technology, like the deployment of space telescopes equipped with extremely sensitive instruments, have revolutionized our capacity to detect and study smaller, Earth-like planets and their atmospheres. Together, these detection techniques form a powerful toolkit that not only locates exoplanets, but also opens a window into their environmental conditions, setting the stage perfectly for investigating their position within the habitable zone and the potential for life beyond our solar system. Now that we can identify exoplanets and glimpse into their atmospheres, the exciting next step is searching for potential biosignatures, chemical signs that might indicate life. These biosignatures go beyond just finding water or oxygen. Researchers look for complex combinations of gases that wouldn't last long without being replenished by biological processes. For example, a mix of methane and oxygen together is particularly intriguing since these gases tend to react and cancel each other out unless some active source keeps producing them, potentially hinting at living organisms. Scientists also consider factors like the planet's temperature, the star's activity, and the atmospheric pressure, which can affect both the chemistry and stability of these molecules. In addition, certain unusual chemicals or patterns, such as seasonal changes in atmospheric composition, could be red flags for biological activity. Future and current space missions aim to push the boundaries of sensitivity to detect these subtle clues, maybe even in the atmospheres of smaller rocky worlds closely resembling Earth. Ultimately, the detection of such biosignatures would not only suggest that life might exist elsewhere, but would also revolutionize our understanding of biology, chemistry, and planetary science, setting the stage for deeper exploration and perhaps one day direct contact. This thrilling pursuit of signs of life takes all the ingenious detection methods into a new realm, transforming distant points of light into worlds with the possibility of living ecosystems, fueling our quest to understand our place in the cosmos. As thrilling as the search for biosignatures is, confirming life on exoplanets is packed with tremendous challenges that scientists continue to grapple with. The first obstacle lies in the sheer distance and faintness of these planets. The signals we detect are often incredibly subtle and can be easily confounded by noise or false positives, such as abiotic processes that mimic biological activity. For instance, certain volcanic or geological phenomena can produce methane or oxygen independently of life, muddying the waters of interpretation. Additionally, our understanding of atmospheric chemistry is still evolving, especially under alien conditions we have never seen before. What looks like a biosignature in one context could be natural elsewhere. Another big challenge is the variability and complexity of host stars. Stellar flares, radiation bursts, and variable outputs can influence atmospheric signals, sometimes masking or altering important clues. Designing instruments sensitive enough to detect and analyze these faint biosignatures pushes the limits of current technology and requires next-generation space telescopes with unprecedented precision. Furthermore, distinguishing seasonal or temporal changes in an exoplanet's atmosphere demands prolonged observation periods, often years or even decades, which is a considerable investment of time and resources. Despite these hurdles, scientific teams keep innovating with new methods like high-resolution spectroscopy and simultaneous multi-wavelength observations to improve confidence in their findings. Each step forward tightens the net around that elusive proof of life, turning what once seemed like science fiction into a tangible scientific frontier. These challenges not only highlight how complex and careful such investigations must be, but also underscore the profound significance of any successful detection, reminding us why this quest drives so much ingenuity and passion in astronomy. This naturally leads us to consider how technological advancements and upcoming missions are poised to overcome these hurdles and bring us closer than ever to answering whether we are truly alone in the universe. Building on the technological innovations spurred by the intense challenges of detecting life beyond our planet, the discovery of exoplanets is fundamentally reshaping the roadmap for future space missions. These discoveries create a powerful incentive for agencies and scientists worldwide to prioritize and develop advanced observation platforms. For example, missions are now being designed with the explicit goal of characterizing exoplanet atmospheres in minute detail, leveraging technologies like large space-based telescopes equipped with advanced spectrometers capable of isolating and interpreting faint signals across multiple wavelengths. The knowledge gained from initial exoplanet surveys informs the selection of target systems, allowing missions to focus on planets orbiting stars with favorable conditions for life, thus increasing the likelihood of meaningful data return. Moreover, the urgency and curiosity sparked by these new worlds are driving investment not only in detection, but also in propulsion and communication technologies, aiming to close the gap between Earth and these distant targets. Concepts such as starshades, which block starlight to better observe orbiting planets, and ultra-precise formation flying spacecraft are transitioning from theory to near-future mission components. In essence, the excitement around exoplanets is a catalyst that accelerates collaboration across international boundaries, bringing together experts from astrophysics, engineering, chemistry, and biology to build comprehensive mission plans. This multidisciplinary approach increases the probability that upcoming ventures will successfully uncover the secrets of these alien worlds. Ultimately, the discoveries of exoplanets transform the goals of space exploration by shifting from mere detection towards nuanced understanding, setting the stage for a new era where answering the big questions about life beyond Earth becomes a tangible mission objective. This continuous feedback loop of discovery informing mission design ensures that as technology advances, so too does our capability to probe deeper, paving the way for future explorers to unlock mysteries that were once out of reach. The remarkable discovery of exoplanets has not only broadened our cosmic perspective, but also transformed the future of space exploration. With each new world found, we refine our tools, sharpen our missions, and deepen our quest for life beyond Earth. This evolving journey from detection to detailed understanding highlights humanity's relentless drive to explore and connect with the universe around us. Subscribe now to stay updated on the latest in space exploration and join the quest for discovering new worlds beyond our own.